Now let's take a look at this theorem. The theorem about general solution for non-homogeneous equations. Suppose y sub p be any particular solution of the non-homogeneous linear nth-order differential equation on an interval like I. Suppose y1, y2, y3, yn be fundamental set of solutions of the associated homogeneous differential equation on interval I. Then for sure you can say that the general solution of the equation on the interval can be written as c1y1 plus c2y2 plus c3y3 plus the rest of them, and you have the last linear combination c and yn for the fundamental set. Then you're going to add the particular solution as well. So recall that how we define the fundamental set. First, we define the Wronskian. Suppose you have some functions f1, f2, f3, fn that has at least the nth minus 1 derivative. Then the determinant of this matrix is going to be called the Wronskian. If this determinant is non-zero, then for sure you can say that you have linearly independent functions. Then we said that as long as these functions are linearly independent from each other, then they form a fundamental set of solutions for the differential equation. Then we can write the general solution for a homogeneous differential equation this way. Now we are extending the idea to non-homogeneous differential equations. So if you have a homogeneous differential equation that has 0 on the right-hand side and y and the derivatives of y are on the other side, then you can find the fundamental set and then write down the general solution this way. Now that we introduce the non-homogeneous differential equations, we are interested in writing the general solution. So again, we are going back to this theorem. If you have a non-homogeneous differential equation, you find the general solution, writing them as linear combination of fundamental set and also particular solution. For example, recall that we showed e to the x, e to 2x, and e to 3x are solutions for the following homogeneous differential equations. We showed that the Wronskian is non-zero and they are linearly independent from each other. And then we showed that y equals to c1 e to the x plus c2 e to 2x plus c3 e to 3x is a general solution for this homogeneous differential equation. And again, remember that all of y and the derivatives of y are on the other side and you have 0 on the right-hand side. Now, if you form a non-homogeneous equation, what I'm going to do, I'm going to add a function like 3x on the right-hand side. So the homogeneous equation has 0, non-homogeneous equation has 3x. We just arbitrarily define this. You can define as many non-homogeneous equations as you want. It happens that y sub p, which is negative 11 over 12 minus a half x, is a solution of this non-homogeneous differential equations. If you take the first derivative of this function, it is negative a half. The second derivative becomes 0. The third derivative becomes 0. So this guy is going to be 0. This is equal to 0. But this one is 11 times negative a half. Minus 6 times this function. If you simplify it, you get 3x on the other side. So indeed, this is a solution for this differential equation, and we show it with y sub p because it is particular solution. What's the meaning of that? It means that there is no c involved in the solution set. There is no c, c1, c2, c3 involved in the solution for this differential equation, and this function is written without any c. So that's why we call it a particular solution versus the general solution that have c1, c2, c3, and so on. So by the theorem, we learned that we can write the solution for the non-homogeneous differential equation as the addition of y sub c and y sub p. But what is y sub c? Y sub c is c1 e to the x plus c2 e to 2x plus c3 e to 3x, and y sub p is negative 11 over 12 minus a half times x. So basically, you are taking the fundamental set solutions, writing the linear combination, and add it to the particular solution. So we take all linear combinations of the fundamental set solutions plus the particular solution, and we define the general solution for non-homogeneous differential equation. This is the equation that we try to solve. So later on, we're going to learn the techniques to actually how to find these fundamental solutions and particular solution for different types of differential equations.